what are the advantages? Huh? You don't try to find the value function. Good. Why?
Because you're working with policies.
Huh? So why is it a good idea not to try to find the value function? Too far back, huh? Old history. People don't remember it. So it could turn out that the value function is a lot more complex in terms of the distribution of the value over the state space than is the policy. So the classical example I give for this is the inventory control problem. So the inventory control problem, essentially the policies that you will be considering are what are called threshold policies, right? If the inventory is below X, you buy. If the inventory is above X, you don't buy. Right? So that's essentially what it will reduce to. The policies will reduce to that. But if you look at the value function, so depending on some kind of a cross product of what are all the things that are available, you will get some very complex function depending on how the rewards are work and so on and so forth, right. So from a representation point of view, it is a lot easier to represent policies in some cases than it is for representing value functions, right. Especially when we go to the parameterized setting, right, you can possibly represent policies with a lot fewer parameters than you can represent value functions, okay, possibly. So that is one advantage, right. So more compact, right. So the second advantage what do you think is the second advantage? Again, when we move to the parameterized forms, right. So value function approximation methods, right, are not guaranteed to converge anymore, right. I mean they work fantastically, so you have DQN and other things, but you really do not have much of a intuition as to how they will converge except in the case of linear parameterization, right, and it's not 100% clear how things will work. But in the case of policy gradient algorithms, so you have some kind of guarantees that they will at least converge to local optima, right, and so that seems to give us a lot more leverage, right, in the sense that you can say, oh, things will be stable, you know, if I keep running this for some time it will converge to something, right. In the case of value function methods, I do not know, it might even diverge, right, it might start oscillating. So I have no guarantees as to the behavior of the methods under value function approximation. So when I am working with really large problems, it might be better off working with policy approximations than with value function approximations, okay. Having said that, I should also point out that almost all the large scale successful applications of reinforcement learning, right, have involved value function approximations, okay. So in theory it's not guaranteed to work, but in practice it does seem to work. Of course you can always come up with examples where things did not work also in practice, right. So you can always come up with very simple examples, like people talk about XOR killing neural networks, right. So you can always come up with very simple counter examples where you can show that value function approximation is really not going to converge, right. Therefore people are always a little wary about doing neural networks and other things until DeepMind came along, and now everybody does neural networks, right. So if you now try to write a reinforcement learning paper without deep networks in it, immediately your chances of getting accepted goes down by 20%, right. So that's how the times have changed, of course, except if you write bandit papers, okay. I mean, so bandit papers do not need deep networks in it, right. So the second thing is I am going to put this in quotes. Better convergence behavior. Okay, so what do value functions method, what do policy gradient methods do? So you actually have some kind of a, I put better within quotes because it's, I mean, In practice, value function based methods also seem to work with the function approximation, but policy gradient you can actually give some kind of a guarantees about convergence local optima. So, what are the problems with policy gradient approaches? We will come to that in a bit. Okay. So, after I describe what we are doing, then I will ask you some questions and then you will know what the problems are. Okay. So, essentially you are going to say my policy pi depends on some set of parameters theta. So, I am always going to write this as, right. So, pi parameterized by some theta, right, and then you have some definition of the performance of the system, right, and then you are going to look at the gradient of the performance with respect to theta and then move in the direction of the gradient, not direction opposite to the gradient, right. So far you have moved in the direction opposite to the gradient because you are minimizing error. Now you are maximizing performance, so you move in the direction of the gradient, right. And then now that it is gradient descent, we all know that it will eventually reach a global or local optima under certain conditions, right. So you have to take small enough step sizes and there are small conditions on the step sizes, and then your gradient estimate should be unbiased or at least biased favorably and so on and so forth. Right. So, if you remember, so we essentially talked about the, right, this is from the reinforced lecture. Right. So, we kept that as the performance measure, right. So, which of course we could not estimate directly because we did not know q star, right. So, we did not know q star, so we could not estimate this directly. So, what did we do? We did a whole bunch of sleight of hand, right. So, we divided this by, we took the gradients, divided it by pi, blah blah blah, and finally we came up with a estimate for the gradient that looked like this. Right. So, where AI is the action you took at the ith sample and RI is the reward you got when you took the action AI. Okay. So, people remember this? This is for the bandit. This is remaining refreshing. See, bandits are so far in the past, right. I thought people would have forgotten all of this, so I am just putting it down here. Great. Now, I want to do this for the full RL problem. I want to do this for the full RL problem. And what is the most straightforward way to extend this? I am sorry? Yeah, okay, fine. So, my policy becomes S comma A. So, my policy now becomes, okay. So, what are my samples? My samples in this case were AI comma Ri, right. So, my samples were
SI.
right. So, what will be my samples in this case?
SI.
Yeah, you have to think a little bit. Yeah, is that the sample or something else the sample? There are multiple ways of doing it, right. So, I am going to give you the simplest form of doing it. Let us go back to the basics, right. So, here the Q function was the average of the rewards, right. What will be the equivalent for writing it in the full RL's case?
Return.
Q function is the average of the returns. So, if I am going to take the average of the returns, so what should be the sample I am collecting? Trajectories, not transitions. It should be trajectories. Yeah. So, I should be collecting trajectories, right. So, my samples will be of the form So, the time being I am going to assume that it ends. Right, I will be collecting trajectories like this. Right. So, now what I can do, I forgot what notation we use for this. I forgot what notation we use for this, but this is GI, which is the return on the ith sample starting from S0, right, and this is the probability of seeing the ith sample starting from S0, right. So, what is this probability Pi? I am starting from S0, the trajectory, right, that S0, A0, R1, huh? The whole probability of seeing, that is the probability of the sample, right. Let's see. So, what did we do here? We said I take action AI and then I am going to get Ri, right. So, this probability of taking action AI is here, right, then I get Ri, right. Here similarly the probability of taking this trajectory is here, and if I take this trajectory then I get Gi, right. Given this trajectory, Gi is, probability of Gi is 1, because the rewards are all fixed in the trajectory, right. Given this trajectory, the probability of Gi is 1, but what is the likelihood that I will actually take this trajectory? Under policy, that is why the theta is here, right. Under this policy pi, what is the probability of me taking this trajectory, right? It is off policy. Off policy learning, when we talked about, it is very similar to the off policy learning, except that there are one policy at the top, one policy at the bottom. The transition probabilities do not depend on theta, they are going to cancel. But if you do a little bit of sleight of hand, I can actually convert the product, it is a product, right, it is a product. If you think about it, it is actually a product term. I can convert the product term into a sum term. It is actually a derivative of the log, right. So, this thing, do not try to write Pi first and simplify it, take this, right. So, now what is Pi? Pi is the probability of taking A0 in S times the probability of going to S1 times the probability of picking A1 in S S1 times the probability of going to blah blah blah, all of those things, right, and times the probability of seeing R1 given you have picked this, all of this is actually a very long product, right. So that product can be written as, so it's ln of the product, right, so it's sum of the lns, so I can write it as the sum of the lns, right. So what will be the term size sum over, will be exactly the ones that I want to cancel out, right. So essentially I will say, okay, sum of ln going from S0 to given S0 A0 going to S1, okay, times the probability of going from S1 A1 to S2. So all of that if I take as one term, they will all cancel out because the derivative will be 0, right. So what will be left out with the probability of taking action A0 in S0, right, the probability of taking action A1 in S1 and so on and so forth. So that will be, those will be the only terms that will be left out, right. So this essentially reduces to, I am not going to work it out, you can do that. Right. You want to take a minute and convince yourself that this is the case. I mean, so write out Pi as a product, right, take the ln, convert that into sums, right, and see which of those will, where the gradient will vanish, right, and then whatever is the left out terms are exactly the ones that I have written there. Right. So even though I do not know Pi because I do not know the transition probabilities, I can write the ratio, or this is called the likelihood ratio if you remember. So I can write the likelihood ratio as just the terms in pi, okay. So here is one small thing which I have kind of any questions on this? So once I estimate the gradient, then I can essentially update my parameters along the direction of the gradient, right. I can do an online update, I can do an incremental update, whatever I want to do I can do. We have various variants of whether I am doing online, incremental, so on and so forth, but that is one thing which I have done a small slate here. I did not explicitly talk about it. If you look at the performance measure eta, right. So performance measure depends, it is a function of theta alone, right? It does not depend on state S or anything like that, right. So essentially here there is no notion of a value function associated with the state, but I still need a notion of a value that summarizes the utility of a policy, right. And what have I done here? Huh? No, what have I done to give a single value for the policy, right. I mean, if you remember the value function case, for starting in every state I had a different value, right, but now I am saying that I will use a single value for the entire policy. So how did I get that single value for the entire policy? What have I done here?
Expectation of return over the policy.
Huh?
Expectation of return over the policy.
The S0 does not have an I on it. I am assuming there is a unique start state, right. I am assuming there is a unique start state and I am using the returns from that unique start state as the evaluation for the policy. Right, this is fine, right. If you think about board games, right, it's always you will start at the same board game, right. A lot of other control things, you will always start at some particular, given a certain amount of resources, and you always start in a particular start configuration and so on and so forth, right. So in many cases this is actually an acceptable thing to do, right, using a unique start state. What happens if you have, instead of a single start state, but you have a set of states over which you can start? Huh? You can take an imaginary start state and with uniform probability you can transition to one of those states without any action, and from there you run your trajectory. So then you look at the value of this imaginary state. We spoke about this earlier also, right. So So, I am basically using this S naught as my unique start state, right. But more commonly there is another assumption that we make for reducing it to a single value function, single value for a policy. So, what is the assumption we make? Sorry. No. Yeah, I mean, as with all Monte Carlo methods, that you need to assume that the trajectory ends here, right. If your trajectory is running on forever, you can't use this method as it is. You'll need to modify it somehow. I'll talk about that in a bit, but that is not the end state is not the issue here. So, there is something else which people do, which is exactly where the average reward RL will fit in, right. So, if you think about it, what does average reward reinforcement learning tell you, right? We already looked at the average reward formulation, right. So, 1 by n as n tends to infinity R1 to, right. So, R1, R2, R3 plus Rn, right. So, essentially you take the average over n steps and then as n tends to infinity you compute that, right. So, if you think about it, because n tends to infinity, any initial variations that you would see in the value for starting in state 1 versus starting in state 2 will all get wiped out, right. Any initial variations will get wiped out because you are summing up a infinite series of numbers. So, as n tends to infinity, the values for starting from any state will average value for a policy starting from any state will converge to the same quantity. So, in average rewards, right. So, you essentially you have only something called rho pi, right. It's like v, the value function v we have. So, in average reward you have value of a policy denoted by rho pi, okay, regardless of what is the state, right. So, rho pi of S we will declare as being equal to the constant rho pi for all S, and that is defined as of course, there are some conditions for all of these average values to exist and be well defined and so on and so forth. So, we are assuming that your MDP satisfies all those conditions, then all you need to do is for a given policy estimate rho pi and use that where instead of GIS naught. Instead of GIS naught you would use rho pi.
We are trying to get over the initial variance by doing this.
Which by doing what?
The average reward.
Yeah, the average reward will essentially, yeah, it's lower variance thing, right. But the point is, well, obviously you are not running it till n tends to infinity, right. So, this is only a sample, right. So, it is a sample estimate. So, the rho pi that I use there will not be the same, it is supposed to be the same, but obviously it will not be the same, just like we know that GIS naught will not be the same, right. So, rho pi is the expected value of this, right. So, I should put the expectation around this. Right. Is it clear? Okay. So, I am not going to get into all the nitty-gritties of this. If I have a lecture, I will go do this. I typically do average reward RL, but almost always I find that 90% of the class does not get it. Okay. So, one lecture is too short a time for me to explain all the nuances of average reward RL. Right. So, I end up teaching the class, but people not actually getting anything from it. So, if you remember that, that is enough for the purposes of this lecture and maybe for actor-critic also later, right. So, any questions, people understand what Monte Carlo policy gradient is? Average reward RL. It turns out that there are some certain convergence results that are easier to prove if you are using average reward RL, one thing. Second, it completely removes the definition, the need for a gamma, right. So, gamma is actually a weird thing, right. For some problems gamma is naturally defined, right. In such cases it is okay to use gamma, but in many cases what happens is you try to artificially define what the gamma should be. Gamma becomes a meta parameter that you tune to get the result that you want, right. So that can lead to all kinds of complications, right. And it also turns out that there is more recent work which well, I also personally have not looked up yet, is showing that function approximation is better behaved with average reward value functions rather than discounted value functions. In fact, there are cases where you can argue that for discounted value functions the target for function approximation is not even well defined, right, which is not the case for average reward value function. So there are many advantages, some of them are theoretical, many of them are theoretical, right, but some of them are also practical in the sense that it is better, it is a certainly a more robust model than using discounts, because when you change the discount factor even slightly sometimes the values can change significantly, right. So that is these are the advantages. The main disadvantages, usually average reward RL is numerically very hard to get it to work. When you implement average reward reinforcement learning and then you try to get it to converge and things like that, it is a major pain, right. So numerically average reward RL is hard to get to work, but ironically it has better theoretical properties. But in this case, well, you need something that is well defined like this, right. It is a single value for the entire policy in case you do not have a S naught, right. And also turns out it is easier to show results for policy gradient when you have average reward things, right. Okay. So there are a whole bunch of caveats and other things which I am kind of sweeping under the carpet. So for example, so I just limit n tends to infinity, right. So what if all your trajectories are only finite length, as we are assuming here, right. What is the definition of average reward if n can never tend to infinity? Well, the simplest answer to it is, well, you always assume that n tends to infinity, right. You always assume that you have a recurrent class of states, right. So which if you get into those class of states with the probability 1, you will stay in those class of states, right. So this is some subset of your state space, so that with probability 1 you will always stay within that set of states, right. If it is a single absorbing state, if you have a single recurrent state, right, not a recurrent class but a single state that has absorbs everything, then at least you assume that you do an infinite number of transitions into that, right. You do not stop the trajectories and your average reward becomes meaningless because it just becomes a reward of that one action, right. So you are assuming that you have a non-trivial recurrent class of states, which is these are the set of states that are of interest. So under this policy you will keep visiting these set of states again and again and you will not stop, right. So only then the average reward becomes more interesting, right. And so this is called okay, let me put this. So and oh man, I do not want to get into more complications. Yeah, let us assume this is, I will just stop here, right. I do not want to talk about other things. If I have time I will do all of that, right. I will do one more detailed lecture on average reward RL, okay. And so any other questions on this? How Monte Carlo policy gradient will work? All of you can go and implement one now. So I can ask you to do policy gradient on the puddle world problem. Are we asking you to do policy gradient on the puddle world? No. Not yet. You fear for your life?
Problem statement already states it as hard.
Huh?
It already states it is very hard.
From the one we gave last time.
Which is the function approximation for Q, is it?
The poor parameterization.
The poor parameterization, and then we ask them for bonus marks, we ask them for a better parameterization, right? No, you don't. I remember asking that. See, they don't want you to get bonus marks. No? There was a suggest better parameterization part to the question. Anyway, so I used to ask the policy gradient version of this question also, right. So run policy gradient on the puddle world, but yeah, so let us not do that for you guys, okay. Fine. So there are a few caveats here. So what do you think would be the biggest problem with this, right? Somebody already mentioned this, I think you mentioned this. What will be the biggest problem with running Monte Carlo gradient estimates like this? The trajectories are very long, right? You will have very high variance. So every time you run the trajectory, I mean you are drawing so many samples for the reward, right? If the rewards, unless the rewards are all deterministic and the transitions are deterministic, so every time you draw a sample, it is going to be different, right? So there will be significant amount of variation in the kind of samples that you are drawing, right? And therefore the variance will be very high, and this is one of the reasons why policy gradient methods typically tend to fail, because the variance is so high, you just have to run these things forever, right? Unless you do something clever to reduce the variance, right? So what do you think you can do to reduce the variance? No, that's not interesting. You can't do that, right? You are essentially having some parameterization theta, and then you change the theta by something, and essentially you will have to say that for every parameterization theta I am going to have a deterministic policy. You will have to come up with a parameterization like that. That severely limits the class of things that you can.
Is it possible to truncate trajectory?
Exactly. So that's what you have to do. Truncate trajectory. The problem is if the trajectories are very long, so make them short. Right? How do I make them short? Huh? Truncate, right? You just say that, okay, I will only do a short term estimate of my return, right? I will not do the full estimate of the return. So why is it okay to truncate it? Anyway, if I have a gamma, the gamma is going to decay anyway, right? If I am using average reward, why is it okay to truncate it? See, if I have done enough circles around the states, right, I would have a good enough estimate of the average reward, right? So I do not have to keep doing this infinitely long for me to get an estimate. Suppose I go 5 times around a loop, right, I will know what is the average reward for that loop is, right? So kind of roughly, right? So I can do that, right? So I can, instead of saying that I will run till time, end of time, which might not happen if I am assuming a recurrent class, right? It might not end at all. I need to have some way of stopping the trajectories. So what typically we do is we say that, okay, here is a unique state, I will start the trajectory from this state. Whenever I re-enter the state, I will stop the trajectory. So that is all. I take a bit of the trajectory, I keep doing this. So this will allow me to reduce the variance. So discounting is one thing, right? So I can, because of discounting, my trajectory will get truncated. The other one is to say that I will designate a unique recurrent state. Whenever I enter the recurrent state, I will stop the trajectory. Even after doing that, if you get long trajectories, what you can do? You can designate multiple states at which you will stop the trajectories. Essentially the idea is to get shorter and shorter trajectories, okay. Yeah, so Sagar, you had a question? Answer it.
The variance was coming from this average return, but the variance was coming actually from P.
From the whole sampling process, yeah. Yeah. So there is another method for reducing variance, right? So where is the variance coming from? Because I am sampling G's, right? So what are G's? The returns, right? So do I know of a way of getting an estimate for G that has a low variance? Huh? Close. Value functions. Value functions are the expected values of these gradients, right? This is the G's, right? So if I know value functions, right, then I have a low variance estimate for the GIs, because every time I do not have to draw the sample, I can look at the average of the samples I have drawn so far and so on and so forth, right. So if I can plug in the value function instead of G, right, some function derived from the value function instead of G's, right, I can reduce the variance of the updates I am making, variance of the estimates of the gradient, right. So that leads us to what are called as actor-critic methods. So the actor is the pi representation, the theta gives me the actor, right. The critic is the guy who evaluates these actions, right. He is the guy who says, no, it's good, bad thing, right? So, the critic. The critic is the guy who I will plug in here, right. So, the critic is used to evaluate the actor, right, and the critic comes from any of my favorite value function estimation techniques, right. I will typically use a parameterization for the critic as well, right. I will use some a function approximation for the critic, and that function approximation will feed into the actor function approximation. I will estimate the actor based on that. So, these are called actor-critic algorithms. So, I will look at actor-critic algorithms later, possibly the next class, but basically I have told you what is the idea behind actor-critic. Now, only the nuances that we will have to think about are how do I actually write this in terms of the value function, right. How do I take out the return and replace it with the value function. So, that is the only thing that we need to think about, as well as there are some technical conditions on the relationship between the parameterization of the actor and the critic, right. I am going to use some function approximator for the actor, some function approximator for the critic, right, and they cannot just be arbitrary function approximations, there has to be some kind of a connection between them. So, these are the two things that you really need to think about. So, we will worry about this in the next class, but right now we will stop here.